from YouTube. This video is created by Nihar from YouTube. What is photodiode? A photodiode is one type of light detector used to convert the light into current or voltage based on the mode of operation of the device. It comprises optical filters, built-in lenses, and also surface areas. These diodes have a slow response time when the surface area of the photodiode increases. Photodiodes are like to regular semiconductor diodes, but that they may be either visible to let light reach the delicate part of the device. Several diodes intended for use exactly as a photodiode will also use a PIN junction, somewhat than the usual PN junction. Some photodiodes will look like a light-emitting diode. They have two terminals coming from the end. The smaller end of the diode is the cathode terminal, while the longer end of the diode is the anode terminal. See the following schematic diagram for the anode and cathode sides. Under the forward bias condition, the conventional current will flow from the anode to the cathode, following the arrow in the diode symbol. Photocurrent flows in the reverse direction. Types of photodiode. Although there are numerous types of photodiode available in the market, and they all work on the same basic principles, though some are improved by other effects. The working of different types of photodiodes works in a slightly different way, but the basic operation of these diodes remains the same. The types of photodiodes can be classified based on their construction and functions as follows. PN photodiode, Schottky photodiode, PIN photodiode, avalanche photodiode. What is a Gunn diode? A Gunn diode is a passive semiconductor device with two terminals, which composes of only an N-doped semiconductor material, unlike other diodes which consist of a PN junction. Gunn diodes can be made from the materials which consist of multiple, initially empty, closely spaced energy valleys in their conduction band like gallium arsenide, GaAs, indium phosphide, INP, gallium nitride, GaN, cadmium telluride, CT, cadmium sulfide, CDS, indium arsenide, INAS, indium antimonide, INSP, and zinc selenide, ZnC. General manufacturing procedure involves growing an epitaxial layer on a degenerate N+ substrate to form three N-type semiconductor layers, figure 1a, wherein the extreme layers are heavily doped when compared to the metal active layer. Further, the metal contacts are provided at either ends of the Gunn diode to facilitate biasing. The circuit symbol for Gunn diode is as shown by figure 1b, and differs from that normal diode so as to indicate the absence of PN junction. Gunn diode. In applying a DC voltage across the terminals of the Gunn diode, an electric field is developed across its layers, most of which appears across the central active region. At initial stages, the conduction increases due to the movement of electrons from the valence band into the lower valley of the conduction band. The associated VI plot is shown by the curve in the region 1, colored in pink, a figure 2. However, after reaching a certain threshold value, VTH, the conduction current through the Gunn diode decreases as shown by the curve in the region 2, colored in blue, of the figure. PIN diode definition. The diode in which the intrinsic layer of high resistivity is sandwiched between the P and N region of semiconductor material, such type of diode, is known as the PIN diode. The high resistive layer of the intrinsic region provides the large electric field between the P and N region. The electric field induces because of the movement of the holes in the electrons. The direction of the electric field is from N region to P region. The high electric field generates the large electron holes pairs, due to which the diode process even for the small signals. The PIN diode is a type of photodetector used for converting the light energy into the electrical energy. The intrinsic layer between the P and N type regions increases the distance between them. The width of the region is inversely proportional to their capacitance. If the separation between the P and N region increases, their capacitance decreases. This characteristic of diode increases their response time and makes the diode suitable for works like microwaves applications. Symbol of PIN diode. The symbolic representation of the PIN diode is shown in the figure below. The anode and cathode are the two terminal of the PIN diode. The anode is the positive terminal and cathode represent their negative terminals. Symbol of PIN diode. PIN diode structure. The diode consists the P region and N region, which is separated by the intrinsic semiconductor material. In P region the hole is the majority charge carrier, while in N region the electron is the majority charge carrier. The intrinsic region has no free charge carrier. It acts as an insulator between N and the P-type region. The I region has the high resistance which obstructs the flow of electrons to pass through it. PIN diode symbol. Working of PIN diode. The working of the PIN diode is similar to the ordinary diode. When the diode is unbiased, their charge carrier will diffuse. The word diffusion means the charge carriers of the depletion region try to move to their region. The process of diffusion occurs continue until the charges become equilibrium in the depletion region. Pin diode let the N-Ni layer make the depletion region. The diffusion of the hole and electron across the region generates the depletion layer across the Ni region. The thin depletion layer induces across N region, and thick depletion region of opposite polarity induces across the I region. Tunnel diode. Definition, characteristics and applications. October 22, 2020 by ELECTRICAL40. It is a tunnel diode. What is a tunnel diode? A tunnel diode, also known as a Saki diode, is a type of semiconductor diode that has effectively negative resistance due to the quantum mechanical effect called tunneling. Tunnel diodes have a heavily doped p-n junction that is about 10 nm wide. The heavy doping results in a broken band gap, where conduction band electron states on the N side are more or less aligned with valence band hole states on the P side. The application of transistors in a very high in frequency range are hampered due to the transit time and other effects. Many devices use the negative conductance property of semiconductors for these high-frequency applications. A tunnel diode is one of the most commonly used negative conductance devices. It is also known as a Saki diode after Ellis Saki for his work on this effect. The concentration of dopants in both P and N region is very high, at around 1024-1025 meters 3. The P-N junction is also abrupt. For this reasons, the depletion layer width is very small. In the current voltage characteristics of tunnel diode, we can find a negative slope region when a forward bias is applied. The name tunnel diode is due to the quantum mechanical tunneling is responsible for the phenomenon that occurs within the diode. The doping is very high, so at absolute zero temperature, the Fermi levels lies within the bias of the semiconductors. Characteristics of tunnel diode: when reverse bias is applied, the Fermi level of the P side becomes higher than the Fermi level of N side. Hence, the tunneling of electrons from the valence band of P side to the conduction band of N side takes place. With the interference of the reverse bias, the tunnel current also increases. When forward bias is applied, the Fermi level of N side becomes higher than the Fermi level of P side, thus the tunneling of electrons from the N side to P side takes place. The amount of the tunnel current is very large than the normal junction current. When the forward bias is increased, the tunnel current is increased up to a certain limit. When the band edge of N side is the same as the Fermi level in P side, the tunnel current is maximum. With the further increment in the forward bias, the tunnel current decreases, and we get the desired negative conduction region. When the forward bias is raised further, normal P-N junction current is obtained, which is exponentially proportional to the applied voltage. The VI characteristics of the tunnel diode is given. Characteristics of tunnel diode: the negative resistance is used to achieve oscillation, and often Zk plus function is of very high frequencies. Tunnel diode symbol: the symbol for a tunnel diode is shown below. Tunnel diode symbol. Light emitting diode, LED. What is it and how does it work? October 28, 2020 by ELECTRICAL40. It is a LED. What is a light emitting diode? LED. A light emitting diode, LED, is a special type of p-n junction diode. The light emitting diode is specially doped and made of a special type of semiconductor. This diode can emit light when it is in the forward biased state. Aluminum indium gallium phosphide, ALINGUP, and indium gallium nitride, INGAN, are two of the most commonly used semiconductors for LED technologies. Older LED technologies used gallium arsenide phosphide, GaAsP, gallium phosphide, GaP, and aluminum gallium arsenide, AlGaAs. LEDs generate visible radiation by electroluminescence phenomenon when a low voltage direct current is applied to a suitably doped crystal containing a p-n junction, as shown in the diagram below. The doping is typically carried out with elements from column 3 and V of the periodic table. When a forward biased current, if, energizes the p-n junction, it emits light at a wavelength defined by the active region energy gap, EG. Working principle of light emitting diode. How does a light emitting diode, LED, work? When the forward biased current, if, is applied through the p-n junction of the diode, minority carrier electrons are injected into the p region, and corresponding minority carrier electrons are injected into the n region. Photon emission occurs due to electron-hole recombination in the p region. Electron energy transitions across the energy gap, called radiative recombinations, produce photons, i.e., light, while shunt energy transitions, called non-radiative recombinations, produce phonons, i.e., heat. The luminous efficacies of typical Alingap LEDs and InGaN LEDs for different peak wavelengths are shown in the table below. The efficacy depends on the light energy generated at the junction and losses due to reabsorption when light tries to escape through the crystal. The high index of refraction of most semiconductors causes the light to reflect back from the surface into the crystal and highly attenuated before finally exiting. The efficacy expressed in terms of this ultimate measurable visible energy is called the external efficacy. The phenomenon of electroluminescence was observed in the year 1923 in naturally occurring junctions, but it was impractical at that time due to its low luminous efficacy in converting electric energy to light. But today efficacy has increased considerably, and LEDs are used not only in signals, indicators, signs, and displays, but also in indoor lighting applications and road lighting applications. Varactor diode definition: the diode whose internal capacitance varies with the variation of the reverse voltage. Such type of diode is known as the varactor diode. It is used for storing the charge. The varactor diode always works in reverse bias, and it is a voltage-dependent semiconductor device. The voltage-dependent device means the output of the diode depends on their input voltage. The varactor diode is used in a place where the variable capacitance is required, and that capacitance is controlled with the help of the voltage. The varactor diode is also known as the varicap, voltcap, voltage variable capacitance or tuning diode. Symbol of varactor diode: the symbol of the varactor diode is similar to that of the PN junction diode. The diode has two terminals, namely anode and cathode. The one end of the symbol consists the diode, and their other end has two parallel lines that represent the conductive plates of the capacitor. The gap between the plates shows their dielectric. Symbol for varactor diode. Working of varactor diode: the varactor diode is made up of N-type and P-type semiconductor material. In an N-type semiconductor material, the electrons are the majority charge carrier, and in the P-type material, the holes are the majority carriers. When the P-type and N-type semiconductor material are joined together, the PN junction is formed, and the depletion region is created at the PN junction. The positive and negative ions make the depletion region. This region blocks the current to enter from the PN region. Reverse bias PN junction diode: the varactor diode operates only in reverse bias. Because of reverse bias, the current does not flow. If the diode is connected in forward biasing, the current starts flowing through the diode, and their depletion region decreases. The depletion region does not allow the ions to move from one place to another. The varactor diode is used for storing the charge, not for flowing the charge. In the forward bias, the total charge stored in the diode becomes zero, which is undesirable. Thus, the varactor diode always operates in the reverse bias. The formula gives the capacitance of varactor diode. Varactor diode equation 1, where mu, permittivity of the semiconductor material. A, area of PN junction, width of depletion region. The capacitance of the varactor diode increases with the increase of N, and the P-type region, and decreases with the increases of the depletion region. The increase in capacitance means the more charges are stored in the diode. For increasing the storage capacity of charge, the depletion region, which acts as a dielectric of the capacitor of a diode, should be kept small. Schottky diode definition: Schottky diode is a metal semiconductor junction diode that has less forward voltage drop than the PN junction diode and can be used in high-speed switching applications. What is a Schottky diode? In a normal PN junction diode, a P-type semiconductor and an N-type semiconductor are used to form the PN junction. When a P-type semiconductor is joined with an N-type semiconductor, a junction is formed between the P-type and N-type semiconductor. This junction is known as PN junction. In Schottky diode, metals such as aluminum or platinum replace the P-type semiconductor. The Schottky diode is named after German physicist Walter H. Schottky. Schottky diode is also known as Schottky barrier diode, surface barrier diode, majority carrier device, hot electron diode, or hot carrier diode. Schottky diodes are widely used in radio frequency (RF) applications. When aluminum or platinum metal is joined with an N-type semiconductor, a junction is formed between the metal and N-type semiconductor. This junction is known as metal semiconductor junction. When aluminum or platinum metal is joined with N-type semiconductor, a junction is formed between the metal and N-type semiconductor. This junction is known as a metal semiconductor junction or MS junction. A metal semiconductor junction formed between a metal and N-type semiconductor creates a barrier or depletion layer known as a Schottky barrier. Schottky diode can switch on and off much faster than the p-n junction diode. Also, the Schottky diode produces less unwanted noise than p-n junction diode. These two characteristics of the Schottky diode make it very useful in high-speed switching power circuits. Schottky diode can switch on and off much faster than the p-n junction diode. Also, the Schottky diode produces less unwanted noise than p-n junction diode. When sufficient voltage is applied to the Schottky diode, current starts flowing in the forward direction. Because of this current flow, a small voltage loss occurs across the terminals of the Schottky diode. This voltage loss is known as voltage drop. A silicon diode has a voltage drop of 0.6 to 0.7 volts, while a Schottky diode has a voltage drop of 0.2 to 0.3 volts. Voltage loss or voltage drop is the amount of voltage wasted to turn on a diode. In silicon diode, 0.6 to 0.7 volts is wasted to turn on the diode, whereas in Schottky diode, 0.2 to 0.3 volts is wasted to turn on the diode. Therefore, the Schottky diode consumes less voltage to turn on. The voltage needed to turn on the Schottky diode is same as that of a germanium diode. But germanium diodes are rarely used because the switching speed of germanium diodes is very low as compared to the Schottky diodes. Symbol of Schottky diode. The symbol of Schottky diode is shown in the below figure. In Schottky diode, the metal acts as the anode, and N-type semiconductor acts as the cathode. The symbol of Schottky diode is shown in the below figure. Metal semiconductor, MS, junction. Metal semiconductor, MS, junction is a type of junction formed between a metal and an N-type semiconductor when the metal is joined with the N-type semiconductor. Metal semiconductor junction is also sometimes referred to as MS junction. Metal semiconductor, MS, junction is a type of junction formed between a metal and an N-type semiconductor when the metal is joined with the N-type semiconductor. The metal semiconductor junction can be either non-rectifying or rectifying. The non-rectifying metal semiconductor junction is called ohmic contact. The rectifying metal semiconductor junction is called non-ohmic contact. History of vacuum diode. November 16, 1904. First vacuum diode was invented by Sir John Ambrose Fleming, and it is also called the Fleming valve, the first thermionic valve. In those days there was no existence of p-n junction in electronics field. A conceptual figure of vacuum diode is shown below. Vacuum diode. How does vacuum tube diode work? Here, the vacuum diode works mostly like a modern diode, but its size is larger. It consists of a vacuum container with cathode and anode inside. This cathode and anode are connected across a voltage source. The anode is applied with positive voltage with respect to cathode. It works on the principle of thermionic emission. A filament heats this cathode. Hence electrons get emitted from the cathode and attracted towards the anode. If the positive voltage applied to the anode is not sufficient enough, the anode cannot attract the electrons emitted from the cathode due to hot filament. As a result, one cloud of electrons gets accumulated in the space between cathode and anode. This is called space charge. Due to this space charge, the further emitted electrons get repelled and come back to the cathode. Hence virtually electron emission stops. No current flows through the circuit. Vacuum tube diode. If the applied voltage between anode and cathode is increased gradually, then more and more space charge electrons come to the anode and create vacant space for further emitted electrons. So with the increase of voltage across anode and cathode, we can increase the emission rate of electrons. At the same time, the space charge gradually vanishes. That means it gets neutralized on the anode. Once for certain applied voltage between anode and cathode, the entire space charge vanishes. There is no more obstruction for emission of electrons from the cathode. Then a beam of electrons starts flowing freely from cathode to anode through space. As a result, current flows from the anode to cathode. Vacuum tube diode forward bias. On the other hand, if anode is made negative with respect to cathode, there is no electron emission from it, as it is cold not hot. Now the emitted electrons from heated cathode do not come to the anode. Due to repulsion of negative anodes, strong space charge will be accumulated between anode and cathode. Again, due to repulsion of this space charge, all further emitted electrons come back to the cathode, hence no virtual emission takes place, hence no current flows in the circuit. So, vacuum diode allows current to flow in one direction only. Vacuum tube diode reversed biased. Under reverse bias, this vacuum diode does not work. This vacuum tube was the basic component of electronics throughout the first half of the 20th century. It was available and common in the circuit of radio, television, radar, sound reinforcement, sound recording system, telephone, analog and digital computers, and industrial process control. Definition: a semiconductor device that generates coherent light of high intensity is known as laser diode. Laser is an abbreviation for light amplification by stimulated emission of radiation. Stimulated emission is the basis of working of a laser diode. Laser diode is similar to LED, however, different from LED. The p-n junction of laser diode produces coherent radiation. Coherent radiation means the light waves generated by the device have the same frequency and phase. Construction of laser diode. The figure below shows the basic construction of a laser diode. Structure of laser diode is formed by doping aluminium or silicon to gallium arsenide material in order to generate N-type and P-type layer. Along with this, an additional active layer of undoped gauze is placed between the two layers. The thickness of this active layer is a few nanometers. The aim of sandwiching this layer in between P and N-type layers is to increase the area of electron and hole combination, resultantly increasing the emitted radiation. The laser output is taken from active region of the laser diode. In laser diodes, polishing at the two ends of the junction is done in order to provide a mirror-like surface. Through reflection from this surface, more electron and hole pair gets produced. Resultantly, that produces more radiation through the device. Working of laser diode. The working of a laser diode involves three processes: absorption, spontaneous emission, and stimulated emission. Let's first understand the process of absorption. Consider two energy levels E1 and E2. For simplicity, let us assume E1 is the lower energy level and E2 is the higher energy level. Absorption in laser diode. Initially, it is assumed that the atom is in the lower energy state, i.e., E1. In order to have transition from a lower energy level to a higher one, the atom requires to overcome the energy difference between the two levels, given by E2 E1. So, some external stimulus is provided to the atom present in the ground state. Thus, an electromagnetic wave of frequency 1/2 is provided to the atom at the ground level. This wave provides sufficient energy to the electron to compensate the energy difference and have transition from E1 to E2. This process is known as absorption. Moving further, now understand the process of spontaneous emission. Spontaneous emission in laser diode. Due to absorption, the atom is present in the energy level E2. So, as the lifespan of the atom expires, it now comes back to ground level from the higher energy level. On coming back to ground level, the atom emits the energy difference of the two energy levels, i.e., E2 E1. This energy is emitted by the atom in the form of electromagnetic wave, generating a photon of energy. This process is termed spontaneous emission. This radiation emission phenomenon is usually seen in optoelectronic devices, such as LED. Us now understand the process of stimulated emission. Stimulated emission of laser diode. Suppose after absorption, the atom is present in the higher energy level, before the exhaustion of its lifespan. So, an electromagnetic wave of frequency equal to the frequency of spontaneously emitted atom is provided to the atom. This causes the atom to perform a transition from E2 to E1. Now, this time the atom will release the energy of two photons in this transition. As we have incorporated the whole junction assembly with a partially reflecting mirror. Thus, this will cause back and forth movement of the atom. Resultantly, this will generate more photons. As soon as the threshold is achieved, photons will get escaped from the mirror surface. A bright coherent radiation is emitted by the device. As at the time of stimulated emission, we are providing a photon energy to the atom. So, the emitted photons will be in the same phase with the incident photons, thus generating a monochromatic bright light. Zener diode definition: a heavily doped semiconductor diode which is designed to operate in reverse direction is known as the Zener diode. In other words, the diode which is specially designed for optimizing the breakdown region is known as the Zener diode. The symbolic representation of Zener diode is shown in the figure below. Zener diode symbol. Zener diode circuit diagram. The circuit diagram of the Zener diode is shown in the figure below. The Zener diode is employed in reverse biasing. The reverse biasing means the N-type material of the diode is connected to the positive terminal of the supply, and the P-type material is connected to the negative terminal of the supply. The depletion region of the diode is very thin, because it is made of the heavily doped semiconductor material. Zener diode connection working of Zener diode. The Zener diode is made up of heavily doped semiconductor material. The heavily doped means the high-level impurities is added to the material for making it more conductive. The depletion region of the Zener diode is very thin because of the impurities. The heavily doping material increases the intensity of the electric field across the depletion region of the Zener diode even for the small reverse voltage. When no biasing is applied across the Zener diode, the electrons remains in the valence band of the p-type material, and no current flow through the diode. The band in which the valence electrons, outermost orbit electron, place is known as the valence band electron. The electrons of the valence band easily move from one band to another when the external energy is applied across it. Zener diode working when the reverse bias applies across the diode and the supply voltage is equal to the Zener voltage, then it starts conducting in the reverse bias direction. The Zener voltage is the voltage at which the depletion region completely vanished. Working Zener diode, the reverse bias applies across the diode increases the intensity of electric field across the depletion region. Thus, it allows the electrons to move from the valence band of p-type material to the conduction band of n-type material. This transferring of valence band electrons to the conduction band reduces the barrier between the p and n-type material. When the depletion region become completely vanished, the diode starts conducting in the reverse bias. Characteristic of Zener diode. The Y characteristic graph of the Zener diode is shown in the figure below. This curve shows that the Zener diode, when connected in forwarding bias, behaves like an ordinary diode. But when the reverse voltage applies across it, and the reverse voltage rises beyond the predetermined rating, the Zener breakdown occurs in the diode. The I characteristic of Zener diode. At Zener breakdown voltage, the current starts flowing in the reverse direction. The graph of the Zener breakdown is not exactly vertical, shown above, which shows that the Zener diode has resistance. The voltage across the Zener is represented by the equations shown below. V equals VZ plus. As applications of Zener diode. The Zener diode is mostly used in the commercial and industrial applications. The following are the main application of the Zener diode. As voltage stabilizer. The Zener diode is used for regulating the voltage. It provides the constant voltage from the fluctuating voltage source to the load. The Zener diode is connected in parallel across the load and maintained a constant voltage VZ, and hence stabilizes the voltage. For meter protection, the Zener diode is generally used in multimeters for controlling the movement of the meter against accidental overloads. It is connected in parallel with the diode. When the overload occurs across the diode, most of the current passes through the diode. Thus, protects the meter from damage. For wave shaping, the Zener diode is used for converting the sine wave into the square wave. This can be done by placing the two Zener diodes in series with the resistance. The diode is connected back to back and in the opposite direction. When the voltage applied across the terminal is less than the Zener voltage, the diodes offer a high resistive path to the current, and the input voltage applied across a diode appeared at the output terminal. When the voltage rises beyond the Zener voltage, they offer a low resistance path and large current flow through the diode, due to which the heavy voltage drop occurs across the resistance and the input wave cut off at the peak. Thus, the square wave appears across the output terminal.